When it comes to utility maximization, first we will talk about utility maximization techniques and utility maximization for different types of utility function, which is Cobb-Douglas, CES utility function, perfect substitute, perfect complement, and quasi-linear utility function. Because like Cobb-Douglas is a special type of CES utility function. Cobb-Douglas is a special type of CES utility function. So the technique that we use for these two are the same. But the technique that we use for these three are different. So we need to use a different strategy or different method to maximize our utility. And also next we will talk about Marshallian demand function, and also how to find Marshallian demand function, the properties, and then we will move to indirect utility function. And also later on we will talk about expenditure minimization and how the expenditure minimization, which is like mean of px such that u is equal to something ux, will give you exactly the same results when you maximize ux such that px equal to m. So either you use expenditure minimization or utility maximization, they will give you exactly the same demand function, which is x. By x we mean demand function. And also when we work on expenditure minimization, we will find out the xh, which is a function of, which is this xh is a function of price and utility, which this one called as a like Hicksian demand function. This one is Hicksian demand function. We derive Hicksian demand function by expenditure minimization. And also we have Marshallian demand function, we just simply write down as a x. Why this one xh? H is taken from Hicksian, the H, the first letter of Hicksian. X is a like economist, so he provided this kind of function. And also just only x is called the Marshallian demand function. For the Hicksian demand function, we use a terminology, and that is unobservable. And observable demand function. But for the Marshallian demand function, we call it observable or normal demand function. Why observable and unobservable? Because in Hicksian demand function, our demand is a function of utility. And we know that we cannot observe utility in terms of like numbers. But Marshallian demand function is called observable demand function because it's a function of P and M. Specifically, it's a function of M or our income. And we can observe our income because we can say, for example, I want to consume like $2,000 this month. I want to consume $2,000 this month. So that's why we use different name for this two demand function. But although when we find out, when we think about or work on expenditure minimization function, we find the Hicksian. When we work on like the utility function, utility maximization, we will move to Marshallian demand function. But because there is duality, as I said, either you work this one, you work this one, you will move to the same result. The thing is, although their graphs are different, but the point that provide you maximum level of utility or minimum level of expenditure, both of them are the same. For example, when you What do you think? Which one has higher slope?
High slope.
High slope.
The yellow one.
The yellow one. This one has high slope. This one shows the Marshallian demand function curve. But more flatter one, it shows the Hicksian demand curve. So although the demand curve for both of them is different, you can see the Marshallian demand function is steeper than the Hicksian demand function. But the point that gave you maximum level of utility, which is the crossing point of two demand function, this one is both. For example, if this one is x1, this one is x, this one is price. When you find out this point is exactly the same for both Hicksian demand function and Marshallian demand function. That's why we say there's a duality exists. Why duality means that either we work by minimization of expenditure function or maximization of utility function, we will move directly to the same level of demand. Although you can see there's different point exist, but as we have like some limitation or constraint, which is our income level, we need to like choose the exact point that maximize our utility and at the same time minimize our expenditure. And it satisfies the income level that we have. But the thing is, why Marshallian demand function is steeper than Hicksian demand function? Because in the Hicksian demand function, this one, let me think. The Hicksian demand function only shows the substitution effect. Substitution effect. Why it only shows the substitution effect? Because for the Hicksian demand function, we have this formula, which is xh is equal to x pu. But the Marshallian, it shows both sub effect or substitution effect, and also it shows income effect. Why it shows both of them? Because the Marshallian demand function x is a function of p and m. The thing is, when we think about substitution effect, what does it mean? It means when the price of something increase or decrease, the price of something increase or decrease, we will move to the substitute option. For example, in case of price increase, when the price of this good increase, we will move to buy the substitute good more. For example, again, let me give you the example of this 2 pen. Although they are substitute, for example, it doesn't mean they are perfect substitute, but they are substitute. If the price of this pen increase, you will move to this pen to buy more amount of this pen and less amount of this pen, because you compare the price of this one to the price of this one. So the substitution effect will comes from the comparison of price of different substitute good. So that's why when the price increase or decrease, you will buy more amount of the substitute product or less amount. If the price of your good, this one, increase, you will buy more amount of substitute product. When the price of this good decrease, you will buy less amount of substitute product and more of this one. So as we only have in this function P, which is price, we only compare the price of two goods here. So that's why this only shows the substitution effect. Because it only shows the substitution effect, so it's flatter, the curve is flatter than the Marshallian demand function. But in the Marshallian, because this one is the function of price and on the same level of income and also at the same time income, so it shows both substitute effect and income effect. So again, substitute effect come from the price comparison. you compare the price of two different goods. But when we talk about income effect, what does it mean? It means that when the price of a good increase, then your purchasing power would decrease. Your purchasing power would decrease. So it means the purchasing power of your income would decrease. Before, by that much amount of income, you could buy more amount of both goods. But now you could buy least amount of one of that goods, which is the price is getting higher. So now the income or the income power to buy goods decrease. So this comes from like the income effect, this one. Because in this demand function, we have both price and income, so it shows more substitute effect and also income effect. But here we only have price. Also we have utility, but utility is not observable. You cannot directly observe the utility. That's why we only think about this P. Because we only have P, so we cannot observe income effect here. So that's why it only shows substitution effect, and it's flatter than this one, because this one shows two effects. So this was about like the duality that we have in expenditure minimization and also in utility maximization. Next, we will move on Shepard lemma and Roy's identity. Shepard lemma and Roy's identity are two ways to find out the optimal amount of demand. By using Roy's identity, we can find the Marshallian demand function. When we have like our indirect utility is given, someone says this is your indirect utility, give me your Marshallian demand function. By using Roy's identity, we can easily find Marshallian demand function. But by using Shepard lemma, we can find the Hicksian demand function. So this is two techniques for finding the Marshallian demand function and Hicksian demand function. For using Roy's identity, we need to have our indirect utility function. Our indirect utility function. But for using the Shepard lemma, we need to have the expenditure function. When we have an expenditure function, we use Shepard lemma to find out the Hicksian demand function. When we have indirect utility function, we use the Roy's identity to find out the Marshallian demand function. This is like two most used techniques. And also these two techniques not only used in consumer theory, we use these two techniques also in producer theory to find out by using Roy's identity, like we can find out the demand from utility function. By using like Shepard lemma, we can find out the conditional demand function of input from our cost minimization function. So they're like very closely related. Utility maximization is closely related to profit maximization. So that's why the way or method that we use for utility maximization, we can use for profit maximization as well. And the way that we use for expenditure minimization, we can use for cost minimization as well. So that's why we can use this formula, Roy's identity and Shepard lemma for both of them. And next we will have the minimetric utility function, which is direct minimetric and indirect minimetric. So this is good because in terms of minimetric utility function, which is related to our income level, so we can observe our utility. So how much amount of utility we will have if we consume this much amount of money. It's more we compare based on money. And finally, we will think about Zlotowski equation, which this Zlotowski equation again comes from duality. Again comes from this duality. Which duality? This duality, which is XPM is equal to XHPU. By this equality, we can find out the Zlotowski equation, which is one of the mostly used equation in microeconomics. So now let's start on utility maximization. So actually, based on the preference axioms, when it comes to utility, which this utility represent our preferences, and also when we talked about utility function and preferences, there was two mostly used axioms if we want to prove the utility function that represent preferences, which was monotonicity and also continuity, and at the same time locally non-associations. Which monotonicity and locally non-associations always say us more is better. We know that more is better. More consumption will provide more utility. But the question is, can we consume goods and services unlimitedly? No, because we have constraint, we have limitation. As we have limitation, we cannot consume as much as we want. What is this limitation? This limitation, our budget. Is our budget constraint. Where this budget constraint comes from? This budget constraint comes from our income level. M, which we can use for income level. Because our income level is limited. So that's why we need to match our consumption level with the amount of money that we have. And also, this is the easiest constraint. Because when it comes to more constraint, most of the time, we have some environmental constraint, we have some legal constraint. For example, in some countries, there are some legal constraints that you cannot consume this much amount, this good from this much amount more. It depends on different contexts. There are some environmental constraints. But in order to work on utility maximization, we just think about budget constraint, which is observable. Because budget constraint is your income level, and you can observe. So that's why when we are going to maximize our utility, for example, U of X, when we are going to maximize our utility, we need to think about a condition which is such that we have some budget for our consumption, for the goods that we use. And that much, this one shows how much amount of money we provide or we pay for the consumption of good of X. P is price, X is good. So the amount of money or the amount of budget that we consume, this should satisfy this condition. It should be less than and equal to our income level. Because in an easy way, we can think about that we cannot consume more than what we have. Income is the things that you have. Consumption is the thing that you want. So you either consume less than what you have or equal to what you have, not more than that. But in order to work easily, mostly we think that there is no saving. And we consume all income that we have. We consume all income that we have. And also if we think in a very logical way, today's saving is tomorrow's consumption. Today's saving is tomorrow's consumption. Because why you want to save? For example, one of the saving that we think about, like pension, the money that we collect for our retirement. So it's a kind of like we save now in order to consume when we get like 65 years old. So why we don't think about saving? Because today's saving is tomorrow's consumption. So what we save today, so we consume tomorrow. So that's why what we saved like 3 years ago, we consume today. What we save today, we consume, for example, 3 years or 5 years later. So that's why we can think easily about this one. Maybe it's not generally correct for the whole individual, for the whole like population, but we think about like that like an average or a representative consumer. So in here, this X is a vector. This X is a vector. It means it's a consumption bundle. It can be X1, X2, Xi, Xj, up to Xn. Up to Xn. And also the P is also vector. Because for each good, we have price. The price of X1, the price of X2, the price of Xi, the price of Xj, and finally the price of Xn. The price of Xn. But our income is not vector, it's just a label. For example, $10,000. And what you need to do, you like allocate this level of income, which is $10,000, to your consumption bundle or consumption vector, which is X1, X2, Xi, Xj, Xn, based on the demand function that maximize your utility. So this one can be allocated to X1, to X2, to Xi, to Xj, to Xn. It means as we have this equality, so you spend all this amount of money to pay this price in order to consume this good. To consume this good. Why you want to do that? In order to maximize your utility, maximize your level of happiness. But the thing is, what are the techniques that can help us to maximize our utility? There is an if condition. For example, it's the necessary condition. Or we can say if condition. What is this if or necessary condition? It says, if there's a big if ux is differentiable if ux is differentiable, it means you can take the derivative. Then you can use the Lagrangian. Lagrangian method in order to maximize the utility. So what do I mean by that? I mean that Lagrangian approach is not a sufficient condition. It's a necessary condition. It can be used only if the utility function is differentiable. And even sometimes, some people say if the utility function is two-wise differentiable. Two-wise differentiable. Why it should be two-wise? Because in the case of perfect substitute, that linear utility function that he said before, that when we use the Lagrangian approach, so there was no solution. Although that function is differentiable, it's one-wise differentiable. You can take the first order condition, but there is no way to take the second order condition. So that's why even for those type of utility function, which they are one time differentiable, you cannot use this Lagrangian method. So if your utility function is differentiable, we can use Lagrangian method. So then our maximum of utility, which is ux, such that px, so now we just think about like equal to m, or again less than and equal to m. So we can like design a Lagrangian. When we design a Lagrangian, we need to clear our choice variable. What are choice variable? We are going to maximize our utility by choosing some optimal level of consumption. Where those optimal level of consumption comes from, those level of optimal consumption comes from consumption of x. Consumption of x. Suppose that in order to make easier, this x is a vector of xi and xj, or this is a vector of x1 and x2. For example, I in 1 and j is 2. So then, this Lagrangian, when we set the Lagrangian, we need to set our choice variable. So here, the choice variable are xi and xj. And also the other things then we need to add here in our Lagrangian terms, or in our Lagrangian choice variable, is the lambda, or the Lagrangian multiplier. Then this one, the Lagrangian function, which is a choice variable, is xi, xj, and lambda. Because what is the lambda? The lambda multiplier, it's like help you to maximize your utility in a way that you spend all your money on your consumption. So we said like this: Lagrangian of xi, xj, lambda is equal to u of xi, xj minus lambda m minus p1 x1 minus p2 x2. So then the first step is to take the first order condition. Is the first order condition. What is the first order condition? The first order condition is the partial derivative of Lagrangian with respect to xi, then the partial derivative of Lagrangian with respect to xj, and the partial derivative of Lagrangian with respect to lambda. So let's do step by step. The first one is the first order condition. The partial derivative of this Lagrangian function with respect to xi, it will come to the partial derivative of uxi xj with respect to xi minus the partial derivative of this term now with respect to xi. Pi xi pj xj. So now, if we take the partial derivative of this term with respect to xi, then what will happen here? So because we only have xi to the power of 1 here. So when we take the derivative of the power of 1, so it will move to 1, because, for example, if we dy with respect to dx and it's equal to, and y is equal to x, so then the derivative of this one is equal to 1 multiplied by x to the power of 1 minus 1. 1 to the power of x to the power of 0. So x to the power of 0 is 1. So 1 multiplied by 1 is 1. So the xi term will vanish from here. So it will just move out. What will happen? So when we take the partial derivative of this one, because we don't have any xi term, so it's 0. When we take the partial derivative of m with respect to xi, because it doesn't have any xi element, so it's also move out to 0. So all this term will remain minus, which is pi. Yeah, this one. I think I made some mistake. This one is positive, this one is negative, this one is negative. Yeah, the other way around, that you make this one is negative, this one is positive,
No, negative.
this one is negative, this one is positive. Then it will work again, because just the sign is like replaced. So now we have only this one, which is lambda multiplied by pi xi. So when we take the partial derivative of this one with respect to xi, it will become to lambda pi equal to 0. The first order condition should be equal to 0. Then again, for this one, the partial derivative of u xi xj with respect to xj now, this one will move to pj now is equal to 0. But now, when we take the partial derivative of Lagrangian with respect to Lagrangian multiplier, so we don't need this part, because there's no Lagrangian multiplier. We only need this part. Then again, when we take the partial derivative of this part with respect to Lagrangian multiplier, so because in each element, the Lagrangian multiplier has the power of 1, so it will become to equal 1. Then what will remain here? It will remain m minus pi xi minus pj xj equal to 0. It's same as you see here, this is same as our budget constraint. Why is same as budget constraint? Just keep like this. M is equal to pi xi plus pj xj. Exactly our budget constraint. So now, this is the first step. The first step is to take the first order condition. So now, the second step is to divide 1 over 2 of first order condition. If this one is 1, this one is 2, so divide 1 over 2. So it will remain to the partial derivative of u xi xj with respect to xi divided by the partial derivative of u xi xj divided by xj. And also, in the other way, we have this one, and we have this one. This one we have for 1, this one we have for 2. If we divide this one, so this lambda multiplier with lambda multiplier will cancel out. Only will remain this one, pi over pj. If you see this formula, something will come to our mind. What is that one? That one is, this the partial derivative of utility function with respect to xi is the marginal utility of xi. So then, instead of partial derivative of utility with respect to xi, we can write down the marginal utility of xi. And also, this one is exactly the formula for the marginal utility of xj. The marginal utility of xj. The marginal utility of xj. And also, this one, pi over pj. Pi over pj. So, again, what is this formula for? Yeah. What is this formula for? Marginal utility of xi divided by marginal utility of xj. Can you remember anything? How we can find the MRS? Marginal rate of substitution. So then, marginal rate of substitution of xi for xj is equal to marginal utility of xi divided by marginal utility of xj. So, this term, our marginal rate of substitution. And also, this is the ratio of prices, price of two goods. And in economics, we say this one as an economic rate of substitution. The ratio of price is called economic rate of substitution. And if you want to know the definition, then you can search it in the internet. So now it's very clear. In order to maximize our utility, so the second step is to divide 1/2 in order to find this relationship, which is marginal rate of substitution is equal to the ratio of price, which is economic rate of substitution. So the step 2, which we divide 1/2, we want to find this one. Marginal utility of xi divided by marginal utility of xj is equal to pi over pj. So then, the third step was this one, color, this one, to set up optimization condition. And that optimization condition is marginal rate of substitution is equal to economic rate of substitution. Marginal rate of substitution is equal to economic rate of substitution. Or another way, the marginal utility of xi divided by marginal utility of xj is equal to the ratio of price. Why is this? Because this one, x1, x2. This one, again, x1, x2. This one is our budget constraint. This one is our indifference curve. So, in the budget constraint, because if you see this budget constraint, the budget constraint is linear. So then the graph for this budget constraint also should be linear. So this is our budget constraint, which is P1 in this case. Let's say this one is xi, this one is xj. Pi xi plus pj xj is equal to income. So how we can find these two extreme points? If, for example, xi is equal to 0, then xj will be equal to m divided by pj, because this one is 0. This one xj is equal to m divided by pj. So it means if you consume 0 amount of xi, you will consume m divided by pj amount of xj. For xi, if you consume 0 amount of xj, you will consume xi is equal to m divided by pi. M divided by pi. And also, this one is your indifference curve. The indifference curve, for example, for a well-shaped utility function, which is Cobb-Douglas and CS utility function, we have this shape. This is our indifference curve. This is our indifference curve. So, the slope, how you can find out the slope of like this budget constraint? The slope of this budget constraint is equal to mpj divided by mpi. mpj divided by mpi. And it's equal to m divided by pj multiplied by pi divided by m. This m will cancel out with this m. So then the slope of this budget constraint is equal to pi divided by pj. The slope of budget constraint is equal to the ratio of price, PI divided by PJ, which is economic rate of substitution. But this indifference curve, so how we can find out, for example, the slope of this indifference curve? The slope of indifference curve, when we suppose we have our x1 here, x1 0, xi 0, xi, xj, xi 0, and xj 0, this point. And if we want to increase, for example, xi 0 to x1 0 to xi1, so then we need to decrease the xj from xj 0 to xj1. So in order to know how much we should increase xi and how much we should decrease xj, we need to know the slope. Again, the slope of this indifference curve at this point. The slope of this indifference curve at this point, which the slope is equal to the marginal rate of substitution, then the marginal rate of substitution xi for xj is equal to the marginal utility of xi divided by the marginal utility of xj. The marginal utility of xj. And at the point that the maximize our utility is the tangent point of indifference curve and budget constraint. So why is that? Because in reality, as we said before, that higher indifference curve will provide a higher level of utility. So when we have like infinite number of like indifference curve. We have too many indifference curve. For example, it starts from here. All of them are indifference curve. But we cannot consume as much as we want in any indifference curve. So what we are doing, we are thinking about to maximize our preference, or in other way, our utility, in a way that satisfies our income level. And that is the tangent point of this true curve, which is this point. This point. If we have this indifference curve, the tangent point is our optimal maximum level of xi and xj. Why we are not consuming in this indifference curve? For example, this one, let's say this one is point B, this one is point A, this one is point C. Why we do not consume point B? Because we have something to consume more. As we say in preference relation, more is better. When we have like the budget, when we have the income, when we have something to use it, so we can move. So by moving further, we can increase our utility level. For example, this one, this point has higher utility this B. This point has higher utility this B. And A has higher utility this B. And also this one also has higher utility, But we need to think about our constraint, which is budget. So we cannot move from one over there. Why? Because they are not like achievable. Why they are not achievable? Because they cannot match our budget. We cannot consume more than what we have. So we need to set our optimal level at the tangent point. At the tangent point. And at the tangent point, the slope of indifference curve and the slope of budget constraint should be equal. So then at the tangent point, which is point A, and point A, the slope of indifference curve is MRS. Yeah? And the slope of budget constraint is economic rate of substitution. This one, economic rate of substitution. This MRS is equal to marginal utility of xi divided by marginal utility of xj, and this ERS is equal to the ratio of price. is equal to the ratio of price. So this is the optimization condition. So now, the third step was which one? Fourth. The fourth step is that to find one of our consumption good as a function of or in terms of another good. For example, we will work on example as well. For example, if we suppose that after setting this equality, suppose we have this relationship. For example, xi divided by xj is equal to like pi divided by pj. What we need to do, we need to find either xi or xj in terms of like pi, pj, and xi. Then we can have our xi as this one. Xi is equal to pi, pj multiplied by xj. The fifth step, the next one, is to substitute to budget constraint. In budget constraint, we have pi xi plus pj xj is equal to m. And now our xi is equal to pi divided by pj multiplied by xj. So instead of this xi, we can write down pi multiplied by pi pj multiplied by xj plus pj xj is equal to m. Then we have only xj here. So we can move out xj to one side and other to another side. And finally, we will find the xj. When we find xj star, for example, anything, suppose that it's equal to something m equal to, for example, pj. Then add this one instead of xj here. Then you will find your xi. And when you find your xj star and xi star, most of the case, both of them are as a function of price and income. As a function of price and income. When your demand function is a function of price and income, it's called Marshallian demand function. So if we define Marshallian demand function, we can say is a demand function that can shows the optimal or maximum level of utility. Or another way we can say the Marshallian demand function is a demand function that can be derived from utility maximization. It can be derived from utility maximization. So this is the most simple definition for the Marshallian demand function. Marshallian demand function can be derived from utility maximization.